Okay, so we'll start with, so we have learned about Simpson's 1/3 rule, right? Previous class. Hmm? So now there is another kind of like, we want to do something more, like more accurate schemes, develop more accurate schemes. So therefore we are learning more types of numerical methods. Okay. So this is one of the last rules I want to cover. Okay. In integration is Simpson's 3/8 rule. You know, like, um, thanks. All right. So this integration is tough. Okay, will be a bit tough. So I'll just show you like why it is tough. Then yeah, we'll see. Okay. So yeah, can you try like using A's and B's here? What should we next do next? Can anyone suggest? Same as 1/3 rule. Obviously, your aim is to find integral y, right? Isn't it? Yeah. So what is this? Sorry, sigma li yi dx. Isn't it? Yeah. So now you have, what is your job? You have to find each li, that is L0, L1. Yeah. So then, and you have to multiply them with the corresponding yi, take the sum. Okay. Then integrate it. Yeah. But these LIs will be very tricky here. Can you imagine why? Okay. So can we write just L0? L0 is, so it is pi. J can't be equal to 0, right? So J has to be 1 to 3, right? And it is x minus xj by, so xi is here 0, right? So that will be x minus x1 by into x minus. Now you can see why it is getting difficult. Okay. You can see that. So the denominators you can easily write. The denominator is easy. Okay, is easy. But the numerator is where you might face the a bit of hard time. Why? Because in the Simpson's 1/3 rule, you did not have this. Okay. Did you have a cubic equation like this in Simpson's 1/3? I ask you to check. Okay. So therefore, so you have to do the integration of L naught. That means you have to do the integration of x minus x1, x minus x2, x minus x3 dx. These are the constants. The denominators are constants and they can be moved outside of the integration. Is it understood? Or see, we um, we after we see an expression, we should not start solving it blindly. You have to analyze. Okay, you have to analyze the function you are seeing. Okay, then you move your pen. Okay, then this is the best approach. Okay, so now you are seeing that L naught, simply L naught, is this guy here. Okay, the denominators you can see, it is x naught minus x1, x naught minus x2, x naught minus x3. These you know, it can be h, it can be 2h, it can be 3h. Okay, but what about the numerator? The numerators are the one you have to integrate. And this integration is not a simple one because it involves like the product of three different linear functions. Okay. So here you have to use, any ideas how to solve this? So you must be knowing product rule of differentiation. So similarly, you should be knowing product rule of integration. So you can take one guy as u and this guy as v. Then you can do integral u into v dx. Rule, Eilert rule. Anyone heard of it? Eilert rule? Yeah. So it is just a tricky thing. Like those who are in maybe class 12th or something and are preparing for competitive exams, they normally use it. I think so. Eilert, like it's giving the chance to who to be the first function, because if you see, I won't reveal the beans here. I will not reveal the secret, but I'll put it to you. Okay. So integral uv dx, it's up to you who to choose u and who to choose v. Okay, like I have chosen u here, v here. You can similarly choose the u to be here and v this. Okay. But depending on the product rule of integration, first integral of second, then yeah. Okay. Yeah. So therefore you should be knowing, so you should make a proper choice of selecting the first function. That's what I'm saying. That's what the catch is. Okay. Here it doesn't matter, but I'm saying a normal product rule of integration. Okay. So if you want this whole thing, the solving this whole thing is there in my notes. But it will be complicated. Okay. I will be skipping this. Okay. But if you want, I can write. Yeah. Okay. So we will use the product rule. Okay. So product rule of integration. So what I have, I just write because it's, sorry. So anyway, I will just write what I have it already solved with me. Okay. You can match. But it's going to be a bit messy. Okay. So I will start with a new page. So that integration, okay. X minus x1, x minus x2, x minus x3. So this is one of the integrations, not the first integration. It might be L1. It might be L1. Okay. So I have done that L1 part by myself. So it will be like x minus x1. Okay. So this is a bit complicated, I know, but this you will get after integration. Okay, this quantity. So similarly, like, yeah. So again, I'm writing another general thing. So this is what I don't want you to understand like much. This you can just say that, yes, you just know the process. Like, yeah, we integrate, we get that formula, but formula is your final thing. Okay, the formula is the final thing. If you don't understand bits and pieces, it's fine. It's totally fine. Okay, you should not expect these to be asked. Understand, like nobody will sit in the exam and solve this bit of messy integration. Okay. So this is the beans. This is the major thing. So integrate anything x0 to x3 li dx. Okay. This generally is of this kind. Bi h cube. I will tell what is bi. Then you go from x0 to x3. That's fine. And you just use the, what do you call that? The Lagrange interpolation polynomial. Okay. You can think why this h cube is coming. Right? You can see why h cube is coming. Because you had three different linear functions and divided by a denominator. Each denominator was having a h. Okay. So all h multiplied 3 times is coming outside. Okay, you have to think when I'm saying. Okay. So bi is the constant you will get because sometimes it is h in the denominator, sometimes it is 2h, 3h, 4h. So you will check, you will see after some calculations that b naught will turn out to be -6, b naught, b1 to be 1, b2 to be -2, b3 to be 6. Again, it's all right, like don't have to go through much details, but this is how they approach or land into Simpson's 3/8 rule. The part of this course is not to feed you much of the math, but you should know how it comes. Then only you can appreciate. If I just tell you that, yeah, this is the final like formula, it's not that interesting. Okay. So anyway, so if you generally, this is the generalized 3/8 rule. This is the important concept. Okay, this is the important one because this is the formula. Okay. So if I'm writing x0 to xn, what is this? If I'm writing x0 to xn, this is the composite 3/8 rule. Previously, I was taking only x0, y0, x1, y1, x2, y2, x3, y3, right? Now I'm taking, so every time you can't have all these 4 points only, right? Your integration will be more efficient if you have lot of points, like 1000 or 100 points, right? So therefore, you have to take x0 to xn. Yeah. So this is known as a composite. So once you start pairing different segments and bring it together, it will be a composite rule. Okay. For that, you have to understand the smallest part. Okay. So again, this is the 3/8 rule. As you see, 3h by 8 is coming. So therefore, it is named 3/8 rule. Okay. Y0 is coming, and then yn will be there. Y0 and yn will be there. Okay. But what is that middle thing is what it matters. Okay. So it will be 3y1, 3y2, but it will be 2y3. Okay. Observe that pattern. So see, how many points we took in the first example? Like here, x0, x1, x2, sorry, x0, y0, x1, y1, x2, y2, x3, y3. Okay. Now you see the pattern here. y0 plus 3y1 plus 3y2 plus 2y3. Okay. So imagine those 4 points in the curve. First point, last point, you leave it undisturbed. Okay. Y0 is there. Then you do 3 times of y1, 3 times of y2. Then the last point is 2 times of y3. Pattern will follow up if you take like, you know, different bunches of further, like there can, here it doesn't stop there. There is yn also. So same pattern, 1, 3, 3, 2. The code, the symbolic sequence, 1, 3, 3, 2. That will follow again and again. Okay. Sorry, the y0 will be there. Y0 and yn you keep undisturbed. The remaining 332, the code 332 again repeat. Okay. So after this 2y3, there will be again 3. Yes. So again 3, 2. Then again 3, 3, 2. Sorry. Yeah. So yeah. So generally writing you will get okay. Yeah. So the whole thing is like, yeah, you don't have to know the process, how it comes, just the steps. How we started the 3/8 rule? So we had like a curve y equals to fx, and we had like 4 points given to us, x0, y0, x1, y1, x2, y2, x3, y3. Okay. Then what we do? Then we use the Lagrange interpolation for each of the segments. Okay. So we found out what are each of the Lagrange interpolating polynomial, LIs. Okay. And then what we said? Then we said that yes, this curve can be approximated by this interpolating polynomial. So taking the integration of that y is same as taking the integration polynomial. Okay. Again, the Lagrange polynomial turned out to be a cubic polynomial here, because the and the integration is a bit tough. Okay, and you don't have to integration. Okay, finally, once you do the integration, you come up to this formula. Okay, so this is how it is. Like, it is 3h by 8 y naught. So you imagine now you have y naught to yn points, x naught, y naught, x1, y1, so on till xn, yn. Okay, then how you will write your formula? This is how you should think. First point, last point, you just add it, keep it there. Okay, this also we will do in the coding part. That's what I did in the last part. I kept y naught and y1, yn as another added and kept in a variable. Leave it undisturbed. Then what I'm doing, then you have to play the game with the patterns game with the remaining set of points in the middle, starting from yn till yn minus 1. Am I correct? Okay. How you will follow that pattern? 3, 2, 2, 3, 2, 2. So this is how you will have this 3-8 rule. Okay. All right. So maybe I just want you to show the code. Okay, so sorry for the spelling mistake there, but yeah, it is Simpson's 3/8 rule. Okay, so I showed you Simpson's 1/3 rule before. So what is this function I'm showing? Last time, if you remember, we took function of the circle x square plus y square equal to 1. Okay, then we took one quadrant of the circle. Okay, and we did 4 times of that integration, so that the aim of this exercise is to compute the value. Okay, to make sure that indeed this method of integration is working. Okay, all right. So like yeah, so have I included something here? Here you can see that I have already given the function f, defined the function f as a lambda function, square root of 1 minus x square. Yeah, so we will apply our integration to this function. Okay, where to where? A to B. We are applying our integration from 0 to 1. See, the numerical integration you have. I'm sorry, but numerical integration cannot give you answers for indefinite integrals. It can give you answer only for definite integrals, because it is numerical. You will have to set the boundaries and it will give you a number. Okay, it can't find integral sine x by x dx. No, it can find 0 to pi sine x by x dx. Okay, so here I have already defined that function, and I'm using the function here fa fb, so you can know what is f. Okay, so again I am integrating same from 0 to 1. I have taken 900 points. Method to work, Simpson's 3/8 rule, the number of points should be a multiple of 3. This is an important point. This you should keep in mind. There is a way that why I did not do 1000. There is a reason why I did not do 1000 points, 900 points. You can do even 999. I have done 900. Okay, so it should be a multiple of 3. Okay, the number of n, it should be n should be a multiple of 3. Okay, for your Simpson's 3/8 rule to work. Okay. Okay, so as I told you, why I have done Simpson 3/8. That's the variable where I am storing the value of integration. Okay, so I am doing fa plus fb. Why? It is following our theory now. It is matching what I have told you in the theory part just before. First and last point, you keep them undisturbed in your formula. Okay, so if you see in our formula, we have y naught and y1, yn undisturbed. Okay. Yeah. So FA, that's the motivation to do FA plus FB. Yeah. Understood? Yeah. So now we move ahead. Why we move ahead? So as to include the remaining points, okay, which had like the sequence 332, 332, okay. So here we are doing for I in range 1 to n, okay. Then what you do, a plus IH. So this is where you are using the uniform spacing. You are starting from A, then you are adding an H, okay, to go to the next point. Then you are adding another H to go to the next point, and so on till you traverse till yn minus 1. Okay. How you do that? Keep on adding H. But there is a for loop going in. So why not you take that advantage? So therefore you multiply I times H. Okay. So every iteration, every for loop iteration, I value is incrementing, and hence you are going to the next point. So every integration, every iteration of the loop, you are going one point ahead. Okay. So yeah. So if I modulo 3 is equal to 0, that means if I is divisible by 3, then what you do? Then you add 2 times that function. Else you add 3 times that function. Okay. Now, can we match this up here? See, pick a term which is divisible by 2. Y3. Yeah. Is it correct? Correct? Yeah. So are you seeing the match between the theory and the code? So now you can appreciate that, yes, we can add 2 times of fx to those guys in which I is divisible by 3. What is the I here? Mind you, I is not this guy. I is the y, the subscript, y3. So 3 is divisible by 3. So therefore, we are doing 2 times of that thing, that point, yi. So 2 times of y3, okay? Else, do 3 times of yi. Finish. Okay, so else you don't have to worry about the others. So that's how cleverly they did. Okay. So it is 3 times of fx. You don't have to worry about other points. Just take the odd man out, put a condition. What is the odd man out here? 2 times of yi was the odd man out. Others were getting multiplied by 3. So don't worry about that other things. Pick that odd man out and apply a, like pose a condition on them, take them out, and remaining you just say 3 times. Okay. So then after you have all of that, we never multiplied 3h by 8. Okay. So that's what we do, Simpson 38 equal to. So you know this meaning of star equal to, right? So that means Simpson 38 equals to Simpson's 38 into 3h by 8. That's a short form of writing. Okay. Okay. Then why we are doing 4 times? See, this is the area of only one quadrant. Okay. For the whole circle, for you to cover the whole, this will be pi by 4. If you don't do 4 times, it will be value of pi by 4, 1 quadrant area. So we have to do 4 times so that 4 quadrant areas are there. 1 quadrant area is the same as other 3 quadrants, right? Am I correct? So it is done 4 times. So again, if you run it, it will be 3.1. Okay. Okay. So this is our question. Okay. So this will be a problem. Okay. Evaluate integral 0 to 6, 1 plus x square dx, 1 by 1 plus x square dx. Okay. I think you already know what's the integration. Okay. Anyone, what's the integration? Sorry. D by dx of tan x. Anyone? Sec x. Okay. Anyway. So this is just a well-known integration. Okay. Try to think. But anyway, we will solve numerically. Okay, without the knowledge. Okay, but using these three rules: A, trapezoidal; B, Simpson's 1/3; C, Simpson's 3/8. Okay. For that, we have to generate our data. Okay. So we have been given a function, but yeah, we can't use the knowledge of function. We will use the knowledge of function, but yeah, we have to get the data in form of points, in the form of x0, y1, y0, x1, y1, x2, y2, and so on, right? So we have to, given this problem, we have to say yes. Let us divide. Okay, let's divide. Let's divide our interval 0 to 6, maybe using h equals to 1. That means it is 0, then 1, 2, 3, 4, 5, and 6. Okay. So there are 7 number of points. Okay. So I'm writing here x. Okay, this is a table. This table. Okay, this is x. This is x, and this one will be f of x. Okay. So 0, 1, 2, 3, 4, 5, 6. Okay. Yeah, can you tell me the values? Yeah. Did not record. So you got one value using, the trapezoidal rule. Okay. Now we'll go to Simpson's 1/3. Okay. Formula h by 3 I equals to, according to Simpson's 1/3 rule. Of course, there will be a h by 3. Sure. Then there will be a y0, which will leave undisturbed. Then of course there will be a y6. Yeah. Hmm? Was y6 there? See, I always told you in Simpson's 1/3 and 3/8 rule, the first value and the last value are undisturbed. So write them first so that their work is done. So now you have to think about other points, the middle points. Okay. So you already know that some will be multiplied by 4 and some. Now go back to your Simpson's 1/3 rule formula, which you have written in the previous class. So odds are getting added and multiplied by 4. Is it? Yes. Then 2 times the even ones. You understood? Again, you can, for y0 to y6, again, you can go to this data and then again put them here just, and you get Simpson's 1/3. So now you can appreciate that how important it is to generate the data first. Okay. Once you generate your data in x0, xi, yi format, then all integration rules are ready. Okay. y1 can anyone say? 0.5, right? Then y3 is 0.1, I think. y5? Yes. Yeah. 0.0385. Okay. Then we are doing 2 times the even, guys. y2, what is y2? 0, y4? 0.058. Compute this. Point 375. 365. Now, Simpson's 3/8. And you just saw the formula, right? So of course it will be 3h by 8 times y0 plus then y6 is there. Okay. Those we leave undisturbed. Then p will be multiplied by 2. So those indices are y3 only. Yeah, am I right? Do you see any other indices multiplied by 3? No. So it will be 2 times y3. Then remaining are multiplied by 3. That's what we did in the programming also. So what are the remaining? y1 plus y2. Okay. That's good. That's how you should do. Okay. So what's this value? Okay. Okay. So yeah. So now here is the main thing. Now can we solve this integration analytically? Okay. So I will go here. Observe this integration. Yeah. Can you solve this analytically? I will ask you this question. What is d by dx of tan inverse x? Okay. So now you know. Okay. Now you know. So how you will solve this analytically? So integration 0 to 6, 1 by 1 plus x squared dx tan inverse x. Okay. 0 to 6. That is tan inverse of 6 minus tan inverse of 0. What's the value you will get? check. Okay. So yeah, make sure, try to think how to compute inverse of some trigonometric function like tan inverse, sine inverse in calculators. It come frequent. Okay. Now 1.4056, this is the analytical result. This result is analytical result. Okay. Whatever we have calculated is the numerical result, right? Huh? So Mr. Dikhil, Mr. Dikhil, can you explain? No. So that's how the thing should happen. Those who don't know should know from the ones who exchange knowledge. Okay. So now, like we have an applied problem. Okay. Previously, we had a mathematical function, and we generated data from the mathematical function. Okay. So now, data set is being given to you. Okay. This data set is from a vehicle. Okay. So the vehicle starts from rest. That means that t equals to 0, velocity equals to 0. Okay. Then the time and velocity are given to you as a data set. For t equals to 2 minutes, your velocity is 10 kilometer per minute. Okay. So on till time t equals to 20 minutes, the velocity has turned to be 0. Okay. Now, the question is, can you estimate approximately the distance, okay, covered in those 20 minutes? Okay. Velocity is being given to you. Yeah. And so where the catch is? The catch is the rate of change of distance is velocity. So that means, suppose x is your distance covered, then dx by dt equals to the velocity. So the end, it has been asked in the question to find the distance. So what you have to do? You have to do integral v dt. Okay. So that's, you can see how the integration is coming into picture. Okay. Now you don't have any function. Now you only have data set. How can you use the methods which I have taught to compute the integration? If you compute the integration, you are getting the distance. So how to integrate, provided that you have been given a data set? Okay. So I have written the Simpson's 1/3 rule here. Okay. So you can see it is h by 3 v0 plus v10. I have left undisturbed. Okay, because these are the first and last points. Okay. Then I have done 4 times the odd parts. That is v1 plus v3 plus v5 plus v7 plus v9. And 2 times the even parts. v2. Okay. So what's the value you are getting? So I consider 2 different examples. One is a function is being given to you. Then you generate the data set from it. Okay. Making it equally spaced. Okay. Then you find the using different rules of integration, you compute the values. Okay. Then next what we did, next, we don't know the function yet. We don't know the function yet. We are just given the data. So from the data, how are you finding the integration? Okay, using different methods. Here we just solved using Simpson's 1/3. Here we just solved using Simpson's 1/3. Some also solved using Simpson's 3/8. So yeah. So I will be giving like similar sort of assignment in this class, okay, for the next class. So we'll discuss about something known as Gaussian quadrature, okay. So just as a starting point, I will say suppose y equals to f of x, and that is just a constant function that is 1. All right. So then I'm asking you to integrate -1 to 1 fx dx. What is this? 2. 2. Okay. So know that this is an exact rule. This is an analytical result you got. Okay. Can you use trapezoidal rule here? Trapezoidal rule. So using trapezoidal rule, IT, suppose, then what you get? It is the area of the trapezoid. Yeah. Half into, again check. Okay. Again check that the value will be 2 using. So that means the analytical and the numerical result are equal. Okay. And why this happened? This happened because your function is a simple one. It's a constant function. So it could easily, like, yeah, the same result you're getting both analytically and numerically. Okay. Now you take fx equals to x. What I tell you? Analytically. Is it correct? See, integral of x dx is equal to x square by 2. X square by 2. Okay. X square by 2 limits are from -1 to 1. For -1, x square, for 1 also x square by 2 has the same value. And you're taking the difference. So it is 0. Okay. Check using trapezoidal rule also you will get 0. Again, both are the same. Analytical and numerical results are the same. Okay. So now you are getting some more knowledge about the trapezoidal rule. That if you are using a constant function or if you are using a linear function, then analytical and trapezoidal rule are giving the same result. Okay. All right. Now things will get different when you take y equals to fx equals to x square. This is not linear. Now compute this. What is this? Yeah. Okay. Now you use trapezoidal rule. What is the answer after using trapezoidal rule? 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. is a good function because you can visualize, even if you don't memorize, like, don't remember the trapezoidal rule, you can just visualize the function, how it looks. Okay. So your function looks like, or like it should be the same. Okay. Can you say now? See, square graph, a parabola. Okay. And it is symmetric. So at x equals to -1, the value of y is 1. At x equals to 1, the value of y is 1. Okay, we have now taken points. We have now taken to use the trapezoidal rule. So it will be just the area of the rectangle. The trapezoid here is like a portion of the rectangle here. Okay, half into, can you say? Yeah. The x-axis, that is 1 minus of -1, that is 2, right? Into the sum of the heights. Imagine a trapezoid. The sum of the heights, FA plus FB. What is FA here? The height of is 1. What is FB here? The height is 1. The same height you are having, 1 and 1. Yes. So it is 2. So this is numerical. How can you see the discrepancy happening? Like previously using analytical form, you got 2 by 3. Now using trapezoidal, you're getting. So now there is something happening. Okay. Only because your function is non-linear. Okay. So now I already told this, like if your function is linear, then yeah, trapezoidal rule and the analytical result will give the same output. Okay. But if your function is non-linear, then yes, they start showing different results. So now accuracy is coming into picture. Okay, now you can easily see why it is the case, because these areas are also computed. Actually, only this area should have been computed, the area between the parabola. Okay, you are computing some extra areas if you are using trapezoid. That's where the error creeps in. Okay, so now, like, okay, you can Simpson's 1/3 rule. Can you find? So without any delay, I can just write it is 1 by 3, 1 plus 4 times 0 plus 1 again. Okay. So you'll get 2 by 3. Okay. So here it matches. Simpson's 1/3 matches. Okay. So now the question is, okay, Simpson 1/3 rule is good. That's okay. But can we modify the trapezoidal rule in such a way that it can give us better results? That's the motivation we get. Okay. Because now you know that yes, trapezoidal rule has not given us the accurate result. Can we modify the trapezoidal rule a bit so that we can get a bit more accurate result? Okay. So the idea is like we want to select. So these are the points which I have selected, A and B. The idea is, can we select not only these? It might not be that only those 2 points A and B give us the result. Might be some other points in the parabola. Okay. So can we find some other point which can give us a better result than the one we obtained? Okay. That's the motivation. So that's the search where it begins. Okay. So this leads us to the path of Gaussian quadrature. Okay. The motivation of finding some other points so that integration will be similar to trapezoidal, but we'll get more accuracy. So it's the same idea. So it's the same idea. Assume that this is x square. Okay. Take some different points. Take different points. It might not be that minus 1, 1. Okay. Some points different, like some different points, like here it is x0 and x1. All right. So some different point. We think that some different point might give us an accurate answer. Okay. It might not be true also. We have to see whether it's true. So idea is, can we write the integration, okay, as sum of like ci f of xi. Okay. So here f of xi means f of x0, f of x1. And associated to them are the constant ci's. Remember the ci's, you already know ci's. Okay. In your, they are the 3 and 2. Okay. So we had the sequence 3, 3, 2. Okay. So those are the ci's. Those constants are the ci's. Okay. So here I am generalizing it. ci's can be some other quantity also. Okay. So this is called generalized version. Okay. The generalized one. Different methods, you will get different ci's. Okay. Okay. So that means minus 1 to 1 y dx is something known as c naught f of x naught plus c1 f of x1. This is very similar to trapezoidal rule, but a generalized version of the trapezoidal rule. Okay. So, yeah. Now we do an experiment, okay? Now we do an experiment. So our task would be to find C0, C1, X1, for which our integral gives us the accurate result, okay? So as a candidate, we can, so this is an experiment we are doing, okay? So as an experiment, you can take different functions, okay? So fx can be like 1, x, x square, x cube. These are our test functions, okay? You need to do it, find out whether they are accurate or not, okay? These are just the test functions, okay? So that we can appreciate it better. Y dx and then your value c0 f of x naught plus c1 f of x1. This is what we want, right? This is what we want. If you compute analytically, these things you can compute analytically. 1x, x square, x cube, you can compute analytically. And this is our quadrature formula, c0 f of x naught plus c1 f of x. All right, for, can you say for y equals to 1, what will be the case? Okay, correct. Then c0 f of x naught is 1, c1 f of x1 is still 1. It doesn't depend, right? Does it depend on the value of x? It's a constant function. For f of x naught, it's 1, f of x1 is also it's 1. So it's c0 plus c1, right? Next, we go to the next candidate x. Can you say this should be 0? Okay. Yes. So can you say now, like, what's the value? So it will be c0, f of x0 is x0. c1, what is f of x1? x1. F of x is, right? So f of x0 is x0, f of x1 is x1. Yeah. So x square, can you say? It's computed 2 by 3. Yeah. But what will be the c0 into x0 square plus c1 into x1 square? X cube, again 0. x0 cube, c1, x1 cube. Now the question is why we are doing this from the first place. Why are we even doing this table? Okay. So the idea is you have here the equation of Gaussian quadrature, like integral -1 to 1 y dx is equals to c naught x naught plus c1 times f of x1. Okay. How many constants, how many naught? You don't know. C1, x naught, you don't know. X1 also you don't know. So there are 4 unknowns. You have to find C0, C1, X0, X1 such that your method is accurate. So there are 4 unknowns. So in order to get those 4 unknowns, you need how many equations? 4 equations. So therefore I have taken the 4. Therefore I have taken the 4 experiments. So 4 experiments are f of x equals to 1, f of x equals to x, f of x equals to x square, and x cube. Okay. I can also take x fourth. Okay. But there are enough unknowns and enough equations, so I stop there. So do you get the motivation now? Like what we are doing actually? Can you see it now? So you just have to solve these 4 equations. Okay, 4 equations and 4 unknowns. So if you do that, uh, right, what are C0, C1, X0, and X1? Can you try? So you now know the 4 equations. What are those 4 equations? 4 we have and 4 unknowns we have, right? So those are like C0 plus C1 equals to 2. X0 plus X1 equals to 0. C0 X0 square plus C1 X1 square equals to 2 by 3. Then X0 cube plus C1 X1 cube equal to 0. All right. So can you solve for C0 and C1, X0 and X1? That's the whole thing. Okay. Yes. So try that, but I will just say it here. You can solve it later. So you will get C0 and C1 to be 1. Okay. X0 you will get like X0 you will be equal to minus X1, and that will be equal to this guy. So what value you have? So integral -1 to 1 y dx, and if you have 2 points, if you have only x0 plus c1 f of x1, this will be equal to f of -1 over root 3, right? Plus c1 is 1 again, f of. So you can check this. If you don't believe, you can check this for all of the 4 cases we have taken. 1, x, x square, x cube, whether this is the case or not. Okay. So yeah. So yeah. So this is just one of the things. Now, if you have 2 points, you have this rule, right? Now, if you have 3 points, so this is the number of points. This is your weights. Okay. So these CIs are because you are multiplying it by a function f of xi. Okay, wi or ci f of xi. Okay, ci are the weights. Okay, and what are the values of x0, x1, and so on. So if you have 2 points, we know the weights will be 1 and 1, right? C0 and C1 are 1 and 1. And what is x0? It will be -1 over root 3. What is x1? It is 1 over root 3. Clear? What happens if you have 3 points? So if you have 3 points, there will be 3 weights and 3 equations. sorry, 3x. Okay. So it will be 6 unknowns. So you have to find 6 equations. So now you can see what you have to do. You have to take, not stop at x3, you have to go x4, x5. Okay. Anyway, that I will not give you trouble. But you can find, I'm just writing it down, that you will find after solving that. These are the quantities, okay? All right. Once you solve. Okay. Now the question is, now you should ask me the question, why are you only solving from -1 to 1? We can get any limit. We can get a to b. We can get 2 to 4. We can get 9. But why are you using y -1 to 1? Okay, so that's not difficult. So what I say is, integral suppose a to b f of x dx, you can always turn into something like -1 to 1 gx dx. Always. The function will be different, but you can always transform. How you do? How you do? Ideas? So you see, not dx actually, my bad. It will be some other variable. It will be some other variable, right? It will be like, say, t, gt dt. Okay? Right? Issues? Yeah? Yeah. So I will just give a comment in the next class regarding this, okay? So in the next class, I will give a comment that how to do this transformation actually.